Good day and welcome to our class again on the proofs of convergent sequence. Today we'll be solving, we'll be proving two or more questions on this. The first one is this: using the definition of limits of a sequence. Show that a the limit as n tends to infinity of the sequence 1 over n equals 0. B, limit as n tends to infinity of the sequence 1 over n squared plus 1 is equal to 0. We want to prove this. We begin from the first one. We want to show that limit as n tends to infinity of 1 over n equals to 0. But it says we should use what? The definition of limit of sequence. So the first thing we do is to try to recall the definition of what? Of limit of sequence. What does that definition say? Recall. It says that what? A sequence an has the limit L, that is, limit as n tends to infinity of an equals to L if for every epsilon greater than 0, there exists a k which belongs to the set of natural numbers such that an minus L is less than epsilon for all n greater than or equals to k. If that is the case, then we need to find what our n is. The first thing we need to do, what our k is rather, is to identify k. That's the first thing we need to do. We want to identify the k that works. So we begin from looking at what? The absolute value of an minus L less than epsilon. Our an, the sequence an as given here, is 1 over L. And the limit L is what? 0. So we have 1 over n minus 0 to be less than epsilon. 1 over n is less than epsilon. But n is greater than k, and k element of natural numbers, therefore k is greater than 0. And if k is greater than 0, it implies that our n also is greater than 0. That means that this becomes 1 over n less than epsilon. We take away the absolute value if n is greater than 0. And so we have what? This implies that 1 is less than n into epsilon. Our 1 over epsilon will be less than n. That implies that n is greater than 1 over epsilon. And if n is greater than 1 over epsilon, since n is greater than or equal to k, as we have said in the definition, it implies that our k is also greater than what? 1 over epsilon. Having gotten a k, or having identified k, we then go back to go and prove the theorem. We go back to go and show that the limit as n tends to infinity of 1 over n equals 0. How do we now show that? To prove, let epsilon be greater than 0. That's as we have said in the definition before. And k belonging to set of natural numbers such that k is greater than 1 over epsilon for all n greater than or equals to k. We want to show that what? Our an minus l will be less than epsilon. Let's go and begin and see whether actually it will be less than epsilon. Remember once again that the sequence an is what? Is a sequence of reciprocals of numbers. So we have it in absolute value, 1 over n minus 0, and that is what? 1 over n. And since we have said that for all n greater than k, and n is element of that, so we have 1 over n. But our 1 over n now, our n, as we have said here, that k is element of the natural numbers, which implies that k is greater than 0. And if k is greater than 0, it implies that what? N is also greater than 0, since n is greater than or equal to k. But our k, as we have found out before and we are using, is that k is greater than what? 1 over epsilon. If k is greater than 1 over epsilon, then we have this to be less than 1 over 1 over epsilon. Since k is greater than 1 over epsilon, our 1 over epsilon is less than k. 1 over epsilon is less than k, and 1 over epsilon, if 1 over epsilon is less than k, then 1 over epsilon will also be what? Less than that. And so that is less than epsilon. This implies what? That our 1 over n minus 0 is less than epsilon, which says that the limit as n tends to infinity of 1 over n is equal to 0. And that is proven. We will quickly take a look at the second one. You can try it and see if you are able to get the same answer, or if you are able to prove it just as I have done. We'll take the second one and see where that takes us. We want to prove that the limit of 1 over n squared plus 1 is equal to 0. Again, remember, we are told to use limit definition. So we are going to recall the definition for limit of sequence. Recall. And what are we recalling? The definition of limit of a sequence. A sequence, let me use xn now. A sequence xn has the limit L if for every epsilon greater than 0, there exists a k which belongs to the set of natural numbers such that the absolute value of an minus l is less than epsilon for all n greater than or equals to k. If we have stated that definition, then the first thing we need to do before we begin to prove it is to identify an appropriate k that works in this situation. We need to do what? Identify an appropriate k that will work in the situation. We want to identify k. For us to identify k, we begin from what? An minus l is less than epsilon. And what's our an in this case? Remember, we are solving the next question, the second one. Limit as n tends to infinity of 1 over n squared minus n squared plus 1. So our an now is what? 1 over n squared plus 1. And our l still remains as 0. So when we put it into the absolute value, we have 1 over n squared plus 1 minus 0 to be less than epsilon. And this gives us what? 1 over n squared plus 1 to be less than epsilon. But remember, we have said that our n is greater than or equal to k. And if n is greater than or equal to k, and k is the set of belongs to the set of natural numbers, it means that what? Our k is greater than 0. And if k is greater than 0, then n is also greater than 0. And that implies that I can remove the absolute value and I have 1 over n squared plus 1. But 1 over n squared plus 1 will be less than what? 1 over n. 1 over n squared. And this is also less than 1 over n. That means our 1 over n is less than epsilon, which gives us that our n is greater than 1 over epsilon. And if n is greater than 1 over epsilon, it means that our k is also greater than 1 over epsilon. If that is the appropriate k that works, we now come back to prove it. Now to prove, let epsilon be greater than 0 and k belonging to the set of natural numbers, which implies that k is greater than 0 for all n greater than or equal to k. We want to show that what? An minus l is less than epsilon. Again, the absolute value of the sequence minus the limit is less than epsilon. That's what we want to show. Our sequence is 1 over n squared plus 1 minus 0. We want to show that this is less than epsilon. 1 over n squared plus 1 minus 0 will give us the absolute value of 1 over n squared plus 1. And this implies what? It implies 1 over n squared plus 1. But 1 over n squared plus 1, as we have rightly stated here, our 1 over n squared plus 1 is less than 1 over n squared is less than n. I'm going to bring that now. That's the k we found. Sorry. We now bring that in. 1 over n squared plus 1 is less than 1 over n squared, which is also less than 1 over n. Therefore, the absolute value the absolute value of 1 over n squared plus 1 minus 0 will be less than what? 1 over n. But remember that our n is what? Greater than or equal to k. N is greater than or equal to k, and our k is greater than 1 over epsilon. Therefore, as we have seen before, n also is greater than 1 over epsilon. By the time we put that there, 1 over n squared plus 1 minus 0 will be less than what? 1 over 1 over epsilon. It implies that 1 over epsilon is less than n. And so if that is the case, 1 over n squared plus 1 minus 0 is less than epsilon. And as such, we have been able to prove that a the absolute value of an minus n is less than epsilon for all n greater than or equals to k. That implies that what? The limit as n tends to infinity of 1 over n squared plus 1 is equal to 0. If you have learned anything in this video, give it a thumbs up, share with your friends, and if you have any questions or you are having trouble or you are having difficulty with any of the proofs, leave your comment in the comment section. Thank you and God bless you.